This is the this is the third video on the lecture series of advanced fluid mechanics. Here from the Reynolds transport theorem, we'll be deriving Navier-Stokes Navier-Stokes theorem, right? Navier-Stokes theorem is the conservation of momentum. As we have seen, the alpha in the Reynolds transport theorem as a property per unit volume. Okay, so if we try to apply Newton's second law, this alpha has to be momentum, right? It will be written as rho v for a unit volume. Okay, so Reynolds transport theorem was this. If you have not seen the derivation of Reynolds transport theorem, please see lecture 1, video number 1, alpha dv equals to, and since I am not referring to any book or not seeing any notes, I am just writing this out of my memory. It's taking some time. You can just uh, increase the speed of video and see these lectures. This is the Eulerian term in the in the Reynolds transport theorem. The right hand side is the Eulerian term. This is the Lagrangian term, right? This is the right hand side. This is the temporal term, and this is the flux term, right? Written with the divergence symbol. For Navier-Stokes, I'm sorry, this will be alpha. For Navier-Stokes, alpha will be replaced by this, so this will become integration of v rho v by dt plus divergence of rho v, another v term, dv, right? Okay, now this is the momentum on a fluid element, right? This is the fluid element. These will have two kinds of forces. One is the surface force, like pressure, stresses. These acts on the surface of the liquid, right? Another force will be body force, like gravity, that acts on the entire volume of the element. Electromagnetic force. Okay? These are forces which act on the entire volume. So this can be written as a surface force, which is defined as surface integral of a notation P, which is the surface force per unit area, and this is the infinitesimal small surface on which P acts, plus the body force which acts on the entire volume. So this is the body force, right? Fb is the body force per unit mass. Now we will take care of this portion and this portion separately, right? So this will be covered in this video itself. This portion we will do in the second video, and in the third portion, the third video, we will see how these two are added uh, to get, not added, equated to get the Navier-Stokes equation. So the left hand side is, now we can change to, this is V. Now we can change to uh, what I call as, or what is known as the index notation. So this is J. J can be X, Y, Z, 1, 2, 3 as per the coordinates, right? Can be R, theta, Z for the polar coordinates, plus D of dxk rho uk uj, right? dv. uh, which can be written as rho duj dt using chain rule, plus uj d rho by dt plus uj, this I'm taking outside, d dxk rho uk plus rho uk duj dxk. Now if we take uj common from these two terms, uj d rho by dt plus d rho uk by dx, this is the continuity equation, and this is equal to 0, right? So only these two terms are remaining on the left hand side. So the left hand side of the momentum conservation equation becomes rho a by dt plus rho uk duj by dx, right? The second video we will see what happens to this term, the right hand side. Thank you.